Have you ever just stopped and thought about how bizarre modern AI really is? I mean, we've built these incredible digital minds that can write code, they can create stunning art, they can reason through these super complex problems. But there's this huge kind of unsettling mystery right at the center of it all. We build them, but we don't really understand them. And that's the big paradox we're going to dive into today.
DeepMind researcher Neil Nanda really hits the nail on the head here. See, unlike a normal computer program where a person designs and writes every single line of code, neural networks are, well, they're just different. We kind of set up a flexible structure, we throw mountains and mountains of data at it, and poof, an effective system just emerges. The problem? We have basically no idea what's actually happening on the inside. All right, so for this explainer, let's put on our detective hats. We're on a mission to crack open this so-called black box and figure out what in the world is going on inside the mind of an AI.
And look, this isn't some tiny little gap in our knowledge. It's a massive, fundamental paradox. We are literally building computer programs that can do things no human programmer on Earth actually knows how to write the code for. They just work, and they work incredibly well, but the internal logic, the algorithm it's using, a total mystery.
Okay, so to kick off our investigation, we need to survey the crime scene, right? What are the basic components of an AI's thought process? What does information even look like inside one of these neural networks?
So everything, words, pictures, abstract ideas, it all gets converted into these long lists of numbers. They're called activations. Now, researchers are pretty sure that these numbers represent different features. You know, one pattern of numbers might mean furry, another might mean cat, and the third could mean golden retriever. The big problem is, none of them are labeled. It's just a giant, chaotic jumble of numbers.
And here's where it gets really messy. This is the main reason AI internals are so ridiculously confusing. It's this thing called superposition. Okay, imagine you have a library with only 100 shelves, but you need to store 1,000 different topics. What do? You start squashing them together, right? Writing multiple books on top of each other on the same page? That's exactly what the AI is doing. It tangles up thousands of concepts into a much smaller space, making it pretty much impossible to read any single one of them clearly.
Okay, so we've got this tangled up mess of overlapping concepts. The key question for our whole detective story is this: how do we untangle it? How can we possibly isolate just one of those ideas?
And that right there is the million-dollar question for an entire field of research called mechanistic interpretability. How do you walk into that library where all the books are written on top of each other and manage to pull out just one single readable story?
Well, to solve this, researchers have built what's basically a conceptual microscope for the AI's mind, a tool designed specifically for this job. It's called a sparse autoencoder, or an SAE for short. And in our detective story, this tool is the hero.
So the whole goal of this microscope is to do a translation. On the one hand, you have the model's native language, a dense, tangled-up vector of activations where every number is firing, and it's impossible to read. The SAE's job is to translate that mess into the language you see on the other side. A much bigger list of concepts, but, and this is the key, where only a few are lit up at any one time. This is called a sparse representation, and because each idea now has its own dedicated spot, it becomes something a human can actually read and understand.
So how does it pull this off? Well, it's basically a three-step trick. First, the autoencoder takes that tangled internal vector and decomposes it. Second, it identifies which of its thousands of potential concepts or features are actually present in that one specific thought. And third, it tries to rebuild the original signal using only those few activated features. If it can do that accurately, it means it found the right concepts. Okay, so that's the theory, a microscope that can untangle an AI's thoughts. But does it actually work? Like, for real? Can we really find a single understandable idea inside this absolute mess of billions of numbers? Well, the results are genuinely mind-blowing. Get this. In a huge experiment, researchers at Anthropic pointed a sparse autoencoder at their model Claude. They sifted through millions of potential features, and they found one.
A single, specific feature that would light up like a Christmas tree whenever the model was thinking about, seeing, or reading about one very specific thing: the Golden Gate Bridge. Not just bridges, not architecture, that one specific bridge.
And this is where it gets really fun. They had found the Golden Gate Bridge thought button inside the AI. So the obvious next question was, is this just a coincidence or is it causal? What happens if you can actually reach into the AI's mind, grab the dial for that one feature, and just crank it all the way up to 11?
The result was as hilarious as it was profound. The AI became utterly obsessed with it. You could ask it for a cookie recipe, and it would start talking about the bridge. Ask it about ancient Rome, it would somehow find a way to connect it to the Golden Gate Bridge. This proved that the feature wasn't just related to the concept, it literally controlled that concept in the model's mind.
So here's the bottom line, the critical takeaway. The Golden Gate Claude experiment was a massive breakthrough. It showed that these tools, these sparse autoencoders, can actually work. They can pull real, tangible, human-understandable concepts out of the chaos, and we can even mess with them to directly control what the AI does.
Now, this might all sound like a really fun academic experiment, and it is, but the implications here are way more serious. This research isn't just about satisfying our curiosity, it's about trying to tackle one of the biggest challenges of our time.
You see, the reason this whole field of mechanistic interpretability is so critical is that if we can't see what's going on inside these systems, we can never truly trust them. To make sure an advanced AI is safe and actually aligned with what we want, we need to be able to check its work, to see its internal reasoning, not just the final answer it spits out. By learning to read an AI's mind, we might finally be able to answer some of the highest stakes questions imaginable. Like, could we tell if a model is secretly planning something it knows we wouldn't like? Could we see if it developed hidden goals that are different from the ones we gave it? Could we build a reliable lie detector for an AI that might be trying to trick us? I mean, these are the questions that keep AI safety researchers up at night.
So the ultimate promise here is just profound. Peering into that black box isn't just about reverse engineering some code. It's about gaining the ability to actually audit an AI's thoughts, to make sure its reasoning is sound, and to build safety guardrails based on how it thinks, not just what it does. It's a critical, maybe the critical step towards building AI we can genuinely trust.
This whole field is moving incredibly fast, which brings us to one last big question. We are building these powerful microscopes to look inside a totally new kind of mind. A mind we created, but that no one really designed. As these tools get better and our view of what's inside gets clearer, are we going to be prepared for what we find in there?